Okay, thermodynamics. Let's look at thermodynamics here. And this talks about the energy of reaction and equilibrium. Recall kinetics, it looks at the reaction rates, how fast they go. Thermodynamics tells us how stable the products are compared to the reactants, which way the equilibrium lies. Kinetics tells us how fast the reaction goes. All right. First, equilibrium constant. We remember this. If you have a reaction, A plus B is in equilibrium with C plus D. The equilibrium constant, products over reactants. Concentration of C times concentration of D divided by the concentration of A times the concentration of B. If we had some stoichiometry here, if we had 2A and 2B, recall those would be the exponents here. The good news is, for the most part, most of our organic reactions are one thing interacting with another thing, especially when we look at the mechanism of the reaction. Therefore, it's usually a one-to-one issue here. Recall, when the equilibrium constant is greater than 1, the equilibrium lies to the right, towards the products. C and D, when the equilibrium constant is less than 1, 0.002, 1 times 10 to the negative fifth, the equilibrium lies to the left. At equilibrium, you have more reactants than you have products. Okay. And remember that whether the reaction lies to the left or to the right can be explained by the change in Gibbs free energy, delta G. So delta G naught, the change in Gibbs free energy, is the free energy of the products minus the free energy of the reactions. Your books likes log, LOG. Most people prefer natural log, LM. So recall that the equation that you will normally see and that I use all the time is delta G naught equals negative RT natural log of K. So delta G equals negative RT natural log of K is one I like to use. If you use just base 10 logs, you have to have an extra factor out there. I just use natural logs. It's more natural. All right. Recall that when K is greater than 1, that means the reaction lies to the right. The reaction is spontaneous. Delta G is negative. When K is less than 1, the reaction lies to the left. Delta G is positive. So spontaneous reactions are ones that the equilibrium lies to the right, and they have a negative delta G. Non-spontaneous reactions, ones that don't go under the current conditions, means the equilibrium lies to the left, and it has a positive delta G. Okay. Enthalpy and entropy. We talked about our enthalpy, the heat of the reaction, endothermic, exothermic. Recall entropy. How random is the system? Recall that nature likes to go towards randomness. So the entropy of the reaction, how random, how many free states, more freedom of motion, more disorder. The higher the entropy, that's the way nature likes it. A positive entropy change means the reaction is more likely to go. Positive entropy change is the way nature likes it. Things become more random. Negative entropy change is when things become less random, and that's not the way nature prefers it. And that brings us to a fairly important equation down here. Delta G equals delta H minus T delta S. Whether the reaction is spontaneous or not, whether it goes forward, the equilibrium lies to the right. Equilibrium constant is greater than 1. Reaction spontaneous. Delta G naught equals delta H minus T delta S, where T is the temperature in Kelvin. And this brings us to a very important part of chemistry. If you recall from General Chemistry 2, when you looked up at tables of delta H values, you noted that the units were all your delta H's around 200, say 2 to 400, let's just go 200 kilojoules per mole. Delta S, when you looked at the entropy values, the S values, you found that S was in the order of about 200 joules per mole Kelvin. Which means, in general, it's a very general statement here, your delta S values being in units of joules, your delta H values being in kilojoules, your delta H is about 1,000 times larger than delta S. Okay. Note you have to take delta S, subtract it from delta H to get delta G. Now we've got to worry about that temperature here, but note room temperature is 298 Kelvin, roughly 300 Kelvin. So this number here for our delta S is going to be 1,000 times less than our delta H number in general. But even though it's 1,000 times less, we're going to multiply it by 300, which means in general, very generally speaking, this whole term T delta S is about 1/3 or less than 1/3 of your delta H term. So even though entropy does play a role, delta H is vastly more important on determining delta G. Delta H has twice, almost 3 times the effect on delta G compared to T delta S. You can change temperature and affect it to get this term to be larger or smaller if you need to. But the take-home message is delta H is much more important to delta G than delta S is, which means if a reaction is exothermic, delta H is negative, which means delta G probably is -2, and the equilibrium lies to the right. Exothermic reactions tend to be spontaneous. If delta H is positive, it's a very good chance that T delta S cannot make it more negative, cannot pull delta G into the negative areas, because this value will be, in general, 1/3 of this value right here. So endothermic overall reactions, the equilibrium tends to lie to the left and towards reactants. It doesn't go. It's a non-spontaneous reactions. So take-home message in your head. In general here, exothermic reactions, equilibrium lies to the right. They're spontaneous. Endothermic reactions, equilibrium lies to the left, non-spontaneous. That's just a general rule to apply. And I can show you exothermic reactions that are not spontaneous. I can show you endothermic reactions, reactions that get cold that are spontaneous. There are exceptions, of course, but in general, exothermic lies to the right, endothermic lies to the left, because delta H is more important for spontaneity than delta T delta S is. Yeah, I think we covered that quite a bit, haven't we? All right. So, recall our energy diagrams. When we did reaction progress, our energy versus reaction progress, here they call it the reaction coordinate. If you've got our reaction, they have it right up here. AB plus C minus goes to A minus plus BC. Note, B was bonded to A, now B is bonded to C. This is a substitution reaction here. We've got to break this bond. That takes energy. Bond breaking takes energy. So this diagram here shows our two reactants, AB and C minus. Takes energy to break this bond. Once the bond is broken, we have the transition state. And that means bonds are starting to get formed afterwards, and that is exothermic. And here, when we look at this reaction, what we see, based just on the diagram here, the way it is drawn, that the energy of our products is lower than the energy of reactants, which means delta H is negative, which means this reaction is exothermic, which means it's probably going to go. The equilibrium most likely lies to the right for this reaction. We know it's exothermic because our products are more stable than our reactants are. Our reactants held more potential energy. That potential energy got lost, got given off as heat when we made these products. Recall that delta H is our thermodynamics. It tells us the heat of the reaction and whether it lies to the left or to the right, the kinetics, whether it's spontaneous or not. the energy from our reactants, level reactants, to the top of the hill to the transition state, when it transitions from mainly bond breaking to mainly bond making, this energy is our activation energy, and that deals with kinetics. The taller this hill is, the larger the activation energy, the fewer the molecules that have enough energy through their collisions to break the bonds that need to be broken, the slower the reaction is going to be. Large activation energy means slow reaction. Low activation energy means fast reaction. And something very, very important to note. If this activation energy were only this tall, if my hill went like this, only up to here and down here, note the equilibrium constant would be the same because delta H would be the same. The spontaneity would be the same, but the reaction would just be a faster reaction. Activation energy has nothing to do with delta H. If you know how fast a reaction is, you do not know, you don't not necessarily know the energy of the reaction. And however, we're going to get into it. There are ways by looking at the kinetics where you can determine the thermodynamics, but the reverse is not the case. But we need to recall some more stuff. Okay, so here, that's what I was explaining. Examples of a slow reaction, but delta H is positive. Here's a faster reaction. Delta H is still positive, still endothermic. The reaction equilibrium lies to the left. And then down here, we've got slow reaction where equilibrium lies to the right. Fast reaction where the equilibrium lies to the right. Okay. So, let's look at some more reactions here. What if our reaction was a two-step reaction? What if the first thing that happened in our mechanism was the AB bond just broke to form A minus and B plus? Note we're looking at this reaction, the same one we were looking at before. But what if during the mechanism we realize that first the AB bond breaks to form this anion and this cation, and then the C anion reacts with this cation to form this two-step reaction. Recall when you add these two reactions together, you'll get the overall reaction. B here is an intermediate, B plus. This B plus moiety is what we call it, a B plus moiety, this B plus beast here, got formed in this reaction and then got used up in a subsequent reaction. It is an intermediate. And when we draw the diagram, we draw it like this, where here you have A and B. The activation energy is energy needed to break the AB bond, which then gives us A minus B plus, and our C was in there. B plus is intermediate. It reacts with the C with a lower activation energy, meaning probably a faster reaction, to form the more stable products. So our intermediate is this little dip. We go up the hill, we have this little dip here, go up a little bit more. Here is our intermediate. All right. Kinetics. We're talking about the activation energy and how fast the reaction goes. Recall kinetics of the reaction. Higher activation energy. The higher the activation energy, the slower the reaction goes. Now we can increase reaction rate with increasing reactant concentrations. The increasing the temperature increases the reaction rate. And recall we have the various rate equations. What we're really going to be looking at is the rate law. Chapter 7 will be dealing with rate laws again. Chapter 8, rate laws. The rate law for a reaction is rate equals K, the rate constant, times the concentration of reactants. Okay, remember all of that from Gen Chem 2. And recall that the rate equation contains concentration terms for only the reactants involved in the rate determining step. When we are doing our mechanisms, recall that the overall rate law for a reaction is the same as the rate law for the slow step. So if we look at the reaction we were doing before, when we see that our first breaking of the AB bond has the highest activation energy, we know this is a much slower step than this. So this is the slow step. Our rate law for that slow step would be rate equals K times the concentration of AB, because in our slow step, AB is our only reactant here. Okay, cool. If you add a catalyst, that will speed up the reaction rate. Now, catalyst speeds up the reaction rate by lowering the activation energy. It lowers the EA. So one way to look at it is if the red curve here is our reaction without the catalyst, and if you add a catalyst, somehow we lower the activation energy. Now, there are two types of catalysts, homogeneous catalysts and heterogeneous catalysts. All right. Let's look at these here. Homogeneous means the catalyst is in the same phase as our reactants. Means if your reactants are dissolved in a solvent, the catalyst is also dissolved in that solvent. Homogeneous catalysts, the catalysts take part in the reaction. Example, see if I can come up with here. Say you had just, you're going to have the reaction AB goes to A plus B minus. Perhaps that reaction doesn't go very quickly, so you add a catalyst. If it's a homogeneous catalyst, AB plus the catalyst would go to something like A catalyst plus B minus. And then the other rule of a catalyst is you have to get it back. So then a catalyst, actually this have to have a positive charge on it, a catalyst plus might then just break into A plus our catalyst back. Remember the two rules of catalyst? They speed up the reaction by lowering the activation energy, and they also come back. You get your catalyst back at the end of the reaction. So here's an example of this A plus B, AB bond, the bond association energy is so high, it's not going to happen, it's not going to break. However, if you add a catalyst, that will break the bond faster, and then the A catalyst bond breaks very quickly also, so that'll speed up your reaction. So that's a homogeneous catalyst. It's in the same phase. You also have heterogeneous catalysts, where the catalyst is in a different phase. And this is most often the case when our catalyst is a solid, and it provides a surface for the reaction to happen on. So most of the time with a heterogeneous catalyst, the catalyst is a solid. It doesn't have to be, but it usually is a solid that provides a surface for the reaction to happen on. And since it's a solid, it stays in there. It doesn't get used up. Our reactants are dissolved in solvent, or they are liquids or gases, and they form their liquid or gaseous products. So you don't form a solid product in this type of reaction usually. All right. Now here's something to remember. Two things very, very important to remember. How does a catalyst affect equilibrium? The answer is the catalyst does not affect the equilibrium. If we go back to this diagram here, the equilibrium is affected by the energy difference between reactants and products. A catalyst lowers the activation energy, therefore the reaction goes faster, but gives you the same products. Since you have the same reactants and the same products, the equilibrium constant is the same. A catalyst does not affect equilibrium. Catalysts just speed up the reaction, meaning we get to equilibrium faster, but they do not affect equilibrium. So that's very important. Catalysts do not affect the equilibrium. They do not affect the energy of the products versus reactants. They only affect activation energy, which tells us about the speed of the reaction. And here's another important thing in kinetics and thermodynamics that we need to discuss, and that is if you look at the equilibrium constant for a reaction, it equals the forward rate constant divided by the reverse rate constant. Recall our equilibrium constant is the concentration of products over reactants. Our rate constants come from the rate laws. Rate equals K times concentration of reactants. And in Gen Chem 2, hopefully you did the derivation to show that the forward rate constant divided by the reverse rate constant equals the equilibrium constant. What this means has a profound effect in chemistry. If you're studying the kinetics of the reaction, and if you happen to know what the forward rate constant is, you figured out what the forward rate constant is, you figured out what the reverse rate constant is. If you know those two numbers, then yay, you can calculate the equilibrium constant. Knowing how fast the forward reaction occurs and how fast the reverse reaction occurs will allow you to calculate the equilibrium constant. However, if you just have the equilibrium constant, you cannot calculate forward and reverse rate constants because they are a ratio. For example, if you knew the equilibrium constant was, say, 100, the forward rate constant could have been 100 million, which means it's a very fast reaction, and the reverse rate constant could have been 1 million. So note, the rate constants of 100 million and a million, that's a very, very fast reaction. Will give you an equilibrium constant of 100 that lies to the right. However, 100 also equals 0.00001 divided by 0.0000001. This also, let's just put in some zeros here to make it clear, this also gives you 100, but these are two very slow reactions. Because the equilibrium constant is a ratio of forward divided by reverse rate constants, just knowing the equilibrium constant cannot tell you how fast the reaction is going. Because equilibrium constant of 100 could be a very, very fast reaction, could be a very, very slow reaction, could be anything. So knowing the thermodynamics does not tell you the kinetics. However, knowing the kinetics can tell you the thermodynamics. Very important. I have a friend who almost did not get his PhD because he refused to believe that. But it's all right here. It's in the math. Get that into your head. All right. So that's it for this chapter, most of which was review. And we will continue with the next video into Chapter 7.